In this example, we are given vector v, and we're told that vector v has an initial point of 16, negative 30, and a terminal point of negative 22, negative 10. And we want to find the component form of v. Now, if you remember, component form of a vector is a way for us to express vectors using an ordered pair. The first component of the ordered pair is just the horizontal displacement of the vector, and the second component of the ordered pair is the vertical displacement of the vector. Now remember, when we write a vector in component form, we have to use the pointy parentheses, not the curvy parentheses. So let's find the horizontal component of this vector. This vector initiates at x equals 16 and terminates when x equals negative 22. So we find that displacement by taking the terminal x value and subtracting from that the initial x value. Now let's find the vertical displacement. This vector starts at y equals negative 30 and terminates at y equals negative 10. So to find the vertical displacement, we take the terminal y and subtract from that the initial y. And that gives us that vector v is equal to negative 38, 20. And these two numbers tell us a couple of different things. The first number tells us the horizontal displacement. The horizontal displacement is negative 38, which means that if I choose any point in two-dimensional space as my initial point, I have to move 38 units to the left. And that would be my first step in finding a terminal point. The second number tells me that I would have to move 20 units up. So if I wanted to recreate vector v with a different initial point other than the 16, negative 30, I can do that. Choose any point in two-dimensional space. From that point, move 38 units to the left, and then up 20 units, and that'll be the terminal point for that vector. So essentially, when a vector is in component form, I have the slope of that vector given to me. The slope will always be the y displacement over the horizontal displacement. So if vector v is placed with an initial point at 15, 8, what would be the terminal point of vector v? Well, we know that if we start at an x value of 15, we have to move 38 units to the left. And we know if we start at a y value of 8, we have to move up 20 units. And if we do those two things, that'll get us the terminal point. 15 minus 38 is minus 23. And 8 plus 20 is 28. So the terminal point of v would be at negative 23, 28. Let's look at this example. Vector v has an initial point p and a terminal point q. So here's point p, here's point q, and those 2 points define the initial and terminal points of vector v. Then we have another vector, vector w, that has initial point r and terminal point s. So these points give us the initial and terminal points of vector w. And we need to find the magnitude of v and w. And then we need to know, is v equal to w? The first thing I'm going to do here is I'm going to take vector v and put it in component form, and vector w and put it in component form. Because what we're going to find out is from component form, we can determine if v is equal to w, and we can determine the magnitude pretty easily. So I'm going to take and put vector v in component form. From the previous example, we know that vector v in component form is equal to the terminal x minus the initial x, comma, the terminal y minus the initial y. And that gives us 27 minus 10 is 17. Negative 6 minus 18 is minus 24. So in component form, vector v is 17, negative 24. And let's do the same thing for vector w. And we'll have terminal x minus initial x and terminal y minus initial y. And we get negative 17, comma, negative 24. So there's the component form of vector w. So if I'm given two vectors like v and w, v is equal to w if and only if they have the same magnitude and they have the same direction. Now, saying they have the same direction is a little nuanced because that essentially means that they have to have the same slope and point in the same direction. So two vectors are equal if they have the same magnitude and if they point in the same direction and have the same slope. But if I put the vectors in component form, it's much easier to tell if they are equal. If two vectors in component form are equal, they will have the same first component and the same second component. When two vectors have the same first and second components, they are equal. So putting vectors in component form essentially answers the question for us, are they equal? Because then all we have to do is look and see if their components match. If they do, they're equal. If they don't, they're not equal. Well, it's plain to see that the first vector, vector v, is 17, comma, negative 24, and the second one is negative 17, comma, negative 24. So these two vectors are not equal. So we could say that v is not equal to w. Now, just for fun, let's find the magnitude of v and w and see if they, by chance, have the same magnitude. Now, remember, when I say magnitude, magnitude is just the length of the vector. And if we look at the length of the vector as the hypotenuse of a right triangle, that means that we can find the magnitude using the Pythagorean theorem. And to use the Pythagorean theorem, all I need is the length of one side of the triangle and the length of the other side, and I can use the length of those two sides to find the length of the hypotenuse, which would be the length of my vector. The great thing about writing vectors in component form is that the first component gives me the length of one of the legs of that right triangle, and the second component gives me the length of the other leg. So in the case of vector v would form a triangle that has the length of one leg, 17, and the length of another leg, negative 24. Now, of course, we know that a leg of a right triangle can't be negative 24 units long. The negative just tells us that the offset is in the negative direction there. That leg would still have a length of 24 units, obviously. So let's find the length of vector v, or the magnitude of vector v. All right, so here's our notation for magnitude of vector v. Anytime we want to find the magnitude, we can notate that just by putting the double absolute value bars around the vector itself. So this is magnitude of vector v, and that is equal to the horizontal offset squared, or the length of one leg squared, plus the length of the other leg squared, and then the square root of that. So that would be equal to the square root of 289 plus 24 squared, which is 576. And that's equal to the square root of 289 plus 576 is 865. For the purposes of this exercise, we don't necessarily have to simplify that radical, because for the purposes of this exercise, we really just want to see if v and w have the same magnitude. All right, so let's find the magnitude of w. That would be the square root of negative 17 squared plus negative 24 squared, which is equal to the square root of negative 17 squared is the same thing as 17 squared, so that would be 289, and negative 24 squared is the same thing, obviously, as negative 24 squared, which would be 576, which would get us the square root of 865. So we see that vector v and vector w have the same length, but we found that they are not equal, which means they must be pointing in different directions or have a different slope.